extremely similar in spirit. I proved this while taking Cameron and Kayla to their first ever dance party. Oh, yes. Yeah, they were too young to go unchaperoned. And so you can tell me if I've made any mistakes in this. Okay, so today we're finally getting to the Riemann Mapping Theorem. So today's going to be, I think, a somewhat leisurely stroll. Did you close the door? So it's going to be a somewhat leisurely stroll. Can somebody remind me what the conditions are? So what are the conditions for the Riemann Mapping Theorem?
Sigma can't be all of C.
It cannot be all of C. So omega is proper, simply connected, proper subset of C. And we saw why we can't take all of C to work. That's Liouville's theorem. And I left for you considering the case of punctured C, why that can't work. And as soon as you say simply connected, if it's punctured, you have to have some kind of path going off to infinity. Otherwise, you will have issues. Okay. One of the big things is always necessary versus sufficient. We'll show that these conditions are sufficient. It turns out they're also necessary by looking at all the possibilities. We haven't talked too much about simply connectedness. It turns out that the conformal image of a simply connected set is simply connected. And so since we'll have to have an inverse map from the disk back to our region, since the disk is simply connected, if we're not simply connected, we can't even play the game. So we need simply connected. We showed that if it's all of C, we have a problem. So we can't have anything better than this. And amazingly, this is enough. Okay. Then there exists a conformal map F from D. Well, you could do it from D, but we'll do it from omega to D. And of course, this means F is complex differentiable, it's infinitely differentiable, the inverse exists, the inverse is complex differentiable. Wonderful. And in some cases, we can even talk about extending the map to the boundary. Okay. So, the proof I'm going to give you is going to start off by using a consequence of the region being simply connected. Because the region is simply connected, I know the existence of a certain function. What function can I define? No. Oh, I mean, I do have primitives, but that's primitive to F, but I don't know what F is.
Log.
The log. So, simply connected implies there exists a logarithm. You can even put like a little subscript omega to remind you that it comes from the region omega. Just because I am using the logarithm does not mean that this is how I have to do it. This is how we're choosing to do it. In general, I believe you do need to use the logarithm. If your set has certain other properties, you can actually bypass the logarithm. So this is the big difference between necessary and sufficient. One of the additional comments today is going to talk about the prime number theorem. We're going to get to the prime number theorem later in the semester. And so, primes, what kind of numbers are primes?
Special.
A little bit weaker than special. If you had to describe it to a 4-year-old, well, okay, to one of my 4-year-olds, or 6-year-olds, what kind of numbers?
Natural numbers?
Natural numbers, integers, right? You should not have to use complex analysis to count natural numbers, right? I want to know how many primes are there less than x. Okay, well, I'm going to define this holomorphic function. Well, a memomorphic function is going to have some poles. I'm going to do some contour integrals. What? Well, we're counting integers. You shouldn't have to do this. So there was a big discussion in the mathematics community. Can you prove the prime number theorem without using complex numbers? And the first proofs in the late 1890s all used complex analysis. And after a while, two conjectures were made about primes. One, you cannot prove the prime number theorem without complex analysis. And two, if you could somehow prove the prime number theorem without complex analysis, boy, would you know a lot. Both conjectures are false. It is possible to prove the prime number theorem elementarily without as good of an error term. And we know much, much less than we do knowing complex. And the reason is complex provides us a lot of powerful tools that we can then use. So we will see that later in the semester. And so I just want you to be aware when we're doing stuff like this, because again, most of you are never going to use the Riemann Mapping Theorem in your life. Or you will use it in such a special case like I do. I use it all the time, but I use it in such a special case I can just prove it directly by writing down the map. What's important is the thought process. How do we get there? Why should we be thinking logarithm? I've got a simply connected domain that's not all of C. Logarithm exists. Okay, so step 1. Map omega 1-to-1 into D. Okay? There's one word in this line that you would love to change one letter. Yes. You'd love to replace that I with an O. Step 2 and step 3 will be replacing the I with an O. Okay? Step 1 is to just say, well look, let's assume that our region lives inside D. This is in some sense standardizing the problem. If we can assume our region is in D, good. We can roll up our sleeves, we have an idea of what we're working with. Regions in all of C that are simply connected, there's lots of different things I could think of. You know, I could maybe have, I miss this going off to infinity. Maybe I miss this going off to infinity as well. That would be okay. That would still be simply connected. And maybe, could I have maybe a spiral over here as well? Would that still be simply connected? That looks like that should be okay. Would that be okay?
They keep spiraling.
What if I draw a closed curve around this? Would I be able to contract that closed curve to a point?
Around?
Yeah, I'd have trouble.
Yeah.
Or another way of saying it is, if I had this curve here, could I somehow move it to that curve, to the dotted curve? No. So I can't have something strange like this. But if this then went off to infinity, then I would be okay. So, you know, I don't want to be considering, let's consider all simply connected regions with just one bad path going to infinity, and we'll proceed by induction, and I'll look at simply connected, you know, you don't want to do something like that. Right? So you want to try to see as much as possible, can you standardize the region? So we will prove step 1. I'm going to first prove step 1 in a very special case that is not enough for what we need. So, step 1, special case. Assume there exists a ball of radius r about some point A whose intersection with omega is empty. I have a simply connected region, that's not all of C. Let's assume I miss a ball somewhere. Okay? Then I'm going to show how to do it. Does every simply connected set miss a ball? No. But if we do miss a ball, things are nice. So imagine, here's my set omega, and here is a ball about some point A that I miss. Without loss of generality, what can you assume A equals?
The origin.
The origin. We can always translate and assume A equals 0. So, without loss of generality, translate by minus A, so can study the ball of radius r about the origin. What's my radius? Okay, and what can I assume about r? What does it equal?
That's one.
I'm sorry?
Any number you want.
Any number. What number do I want? I heard epsilon and I heard 1. I like 1. Why would you like 1? I'm trying to map into the unit disk.
But you
Right?
can't assume that.
Well, but now what I can do is I translated by minus A. I first sent omega to, we'll call it Fa over omega, which I just translated by A. So now let's dilate. Without loss of generality, dilate by what? It's either, well, whatever the original radius was, r. I dilate by 1 over r. Dilate by 1 over r, so and study the ball of radius 1 about the origin. And so now we sent omega to omega minus a, and now we send it to omega minus a divided by r. So those are very simple maps. Those maps are onto the image, those maps are one-to-one, nothing to worry about. So we've just standardized the problem. So now we have a disk of radius 1, and we have the set omega. Can you think of a one-to-one map that will take the set omega into the disk? I want to somehow map omega into the disk. Holomorphically, of course. Where does omega live relative to the unit disk? On the outside. So how can I map outside to in? 1 over, yeah, use the 1 over map. Use the 1 over map. F of z is 1 over z. And that maps the outside to the inside. And so now, our final map would be g of z would be, I think, z minus a divided by r inverse. I think it would be r over z minus a. And so we've now mapped our set into the unit disk. Okay? We can actually do a little bit better if we want. It would be really nice if a certain point in the unit disk was hit. What point would you love to be hit?
The origin.
The origin. Is this going to guarantee that we hit the origin? No. Absolutely not. In fact, will we get the origin? So, I'm quite convinced we will not get the origin if we just use this map. So we now have a map into the unit disk, but it doesn't get the origin. Do we have any way to move things around to get to the origin?
Yes.
What function?
Psi.
Yeah, so let alpha be in the image above, and now we just apply C of alpha. And now we've mapped it into the unit disk, and 0 is attained. Okay? So we can really standardize things pretty well. Okay. So any questions about step 1? This isn't that bad. We're basically just trying to limit our universe of discourse to just mapping subsets of the unit disk to the unit disk. And if I give you a subset of the unit disk that's simply connected, can I somehow inflate it up to fill up the whole unit disk? To me, that seems like a lot more manageable problem. You're blowing up a balloon, you're trying to just expand the set a little bit to fill the whole thing. Infinitely differentiably, of course. The problem, of course, is this is not the full strength of the Riemann Mapping Theorem. So you have two options. One option is to say, oh yeah, but all the sets I'm going to study will always be missing, a disk somewhere, and there's no need for that stuff. That is the route to the engineering side. Okay? The other route is to say, well, okay, can I modify this idea somehow? And this is where things get a little bit more complicated. And this is where we will use the logarithm function. And so, this is not the most enjoyable lecture to give, trying to remember all the different steps. So, step 1, using logarithm.
Is this step 1 and then step 1?
No, this was step 1 special case.
Oh, I see.
Now we've left step 1 special case, and now we're just doing step 1 general.
Okay.
Okay, so I want to say, I think it's alpha is the point the book uses that's missed. Yes. Okay. Without loss of generality, let alpha not be an omega. Why can I say that?
Sigma is not all of C.
Omega is not all of C. So because omega is not all of C, there has to be some point that's missing. We've got to give that point a name. Why not call it alpha? So we can define a logarithm. And so because we can define a logarithm, that logarithm will involve omega. I'm not going to do too much notation. So there exists a logarithm. So we can define the log of z minus alpha on omega. Okay, and then I think they're calling this little f. No. Yes, they're calling this little f. Call it f of z. Alright, so there's a nice function that whenever you see the logarithm goes hand in hand with the logarithm. The exponential. So note, e to the f of z is what? It's z minus alpha. Okay? Now, the question is, what kind of properties do we have about the logarithm? The exponential is, can two different numbers give me the same logarithm? Say z does not equal w. If f of z equals f of w, then e to the f of z is e to the f of w. But what's e to the f of z? So z minus alpha equals w minus alpha. So z equals w, contradiction. So we've just shown f is 1 to 1. Therefore, f is 1 to 1 holomorphic. Because if two different inputs went to the same output, contradiction. Now, we've got to be a little bit careful. A little bit more is true. So clearly I can't have f of z equals f of w, or I get a contradiction. But there's something else f of z can't equal relative to f of w. So I use the exponential. Is the exponential function 1 to 1? Can two numbers have the same exponential? So if you think of e to the z, yes, what two numbers would have the same exponential?
E to the 0 and e to the 2 pi I.
Ah, so unfortunately the exponential function is not 1 to 1. That didn't really matter here. Okay. Well, let's see. So instead of saying f of z equals f of w, how could I expand this? If f of z equals f of w plus... plus what? It's not pi I. Pi I is close.
2 pi I.
2 pi I is not quite right. It's close. 2 pi I n.
Oh, yeah.
If it equaled 2 pi I n, then their exponentials would be the same and we would have a contradiction. So we get a little bit stronger. So fix w in omega. For all z in omega, f of z does not equal f of w plus 2 pi I n for any n. Okay? So we're getting some idea of what points we have, of what things look like. Could we be, right now, haven't really prepared this lecture, kind of doing it on the fly, trying to get a sense of what things look like. We know f of z can't be the same as f of w. It can't be f of w plus 2 pi I n. How close do you think it could be to f of w plus 2 pi I? So, how close could f of z be to f of w plus 2 pi I. We're just doing the n equals 1 case. Why don't I want to do n equals 0? That's the easiest case to look at. Why don't I want to ask, how close could f of z be to f of w? Yeah, take z to be w. Right? So clearly, we don't want to consider n equals 0. You know, can f of z be really close to w? Yes. How can we do it? Make z equal w. Oh, okay. Right. That case is not. So the first interesting case is f of w plus 2 pi I. Could we be really close to that? So imagine we have a sequence zk such that f of zk is converging to f of w plus 2 pi I. What does that immediately imply? Remember, f is the logarithm. So what function is always in your mind paired with the logarithm? The exponential. So if the logarithms are approaching these, what else must be approaching? The exponentials. Therefore, e to the f of zk has to be approaching e to the f of w plus 2 pi I. Oh well, that's just e to the f of w. What's e to the f of zk?
zk minus alpha.
So zk minus alpha is converging to
Omega minus alpha.
omega minus alpha. Therefore, zk is converging to w. And remember, zk and w, they're all interior points. This is very important. Omega is open. We might not have put that in our conditions. Omega is open, so w is in the interior, which is in fact all of omega. I've got zk approaches w, and f of zk is going to f of w plus 2 pi I. But f of zk is converging to f of w plus 2 pi I. How does that make you feel? I'm sorry?
Is that a constant equation point?
Oh, not quite constant.
Isn't that a contradiction?
It's a contradiction.
It's discontinuous.
As you get closer and closer and closer to w, your value gets closer and closer and closer to f of w plus 2 pi I. This violates continuity. Okay? So, can f of z be close to f of w plus 2 pi I? What does it mean by saying it can't be close?
It has to be f of w.
I'm sorry?
It has to be f of w plus 2 pi I.
Well, we know it can't be f of w plus 2 pi I, and we just showed that we can't have a sequence zk such that f of zk converges to f of w plus 2 pi I. So we need to figure out, what does this mean? What have we just proved?
W plus 2 pi I is not in the image of the function.
So w plus 2 pi I is not in the image of the function. So I want to try to keep this stuff on the blackboard. So let's try to write things down. Here's my omega. Here's some alpha. I'm applying some function f. This is my log function. And here is some special point w. Here's f of w. Here's f of w plus 2 pi I. And we've just shown we can't have a sequence of points such that their image under f approaches f of w plus 2 pi I. So tell me in terms of either math symbols or pictures, what does that mean? I'm sorry?
Like if you draw the image, it's on the outside of it,
Okay, outside of what? Outside of a point?
and not in the interior of the image.
So this point is not in the interior of the image, but you can do a little bit better.
It's a ball.
There's a ball about this point that we omit. Why is there a ball about this point that we omit? If not, you give me any radius, and I can always find some point whose image is on that circle. And that would give me a sequence of points approaching. We can't have a sequence of points approaching. Therefore, there must be some radius such that inside that radius about this point, no points are sent by f there.
Would this work for other multiple pi I?
Yes.
That the paint there would be infinitely many.
There are infinitely many that we can do. Yes. And so the reason we're doing n equals 1 is because it is the simplest choice we can do. Other than n equals 0, which we could do, but is useless. Okay? But this is, again, I want you to see why the book is doing things. Do we all agree now that there is some ball about f of w plus 2 pi I that we never hit? Nothing, never in here. Okay, so maybe this is now f of omega. I don't know. Looks something like this. If you stare at this long enough, something should look familiar.
It's connected.
It's simply connected. What else?
It's just the special case.
It's the special case! Remember, there should be an email. This is the special case. Right? I said, imagine we were fortunate enough to have a situation where we had a ball that was omitted. Then we're done. We have a ball that's omitted. We now translate, and we now invert. Okay? It's really just a special case. If you go back to Calc 1, okay, a long time ago, okay, do you remember the mean value theorem? One of my favorite theorems in Calc. What's the special case of the mean value theorem?
The interval 0 to 1?
Believe
sorry?
I can't hear you.
The interval from 0 to 1, maybe?
No, there's a special name for a very special case of the mean value theorem. Oh, whose theorem? Wilson, thank you. I knew it was not Ushay's theorem. I know it starts with an R, and I've just been doing complex too much this past few weeks. We have Rolle's theorem, right? If you have a function whose derivative is 0 at the two endpoints, then there must be some point in between where the derivative is 0. If you can do that special case, you can do the mean value theorem by just translating your function and rescaling. So if you can understand Rolle's theorem, you understand the mean value theorem. I believe Rolle was famous for attacks on calculus, and it's kind of amusing if so that he's now only remembered for a calculus theorem. But it was legitimate to criticize calculus. Calculus was not built on firm foundations. It took a while before calculus was done properly. So this is an idea you've seen before in other classes. Do a special case, reduce to the special case. The special case was omitting a disk. If you omit a disk, it's trivial. Use the 1 over function. The difficulty is taking the general case and getting to the situation where you can use the special case. And that's what I wanted to really emphasize. Now we know how to finish step 1. Okay. Now we're in the special case. Okay. So now we're happy, right? Step 1 of 3 is done. To recover from doing too much alcohol takes 10 steps. This takes 3 steps. But the second step, I think, is a lot worse than recovering from alcohol addiction. Okay. Can someone tell me what step 2 of the Riemann Mapping Theorem is?
Just translating it to the origin.
Okay, so technically we should do that as well. And we should then say that we've translated our set so that it includes the origin. So part of step 1, I'm going to assume we now have 0 inside. So we will be in the situation now where we can assume 0 is in omega, is a subset of the disk, is simply connected and open. So what was step 2? So if you can't tell me what step 2 is, you have not prepared well enough for class. Okay? You should at least know what step 1, what step 2, what step 3. If we are going to have any chance of you enjoying the next few lectures, you have to be prepared for class. There is too much terminology. There is too much detailed calculations. If you have not read the notation before, unless you are very different than I am, the lectures will be very hard to follow. I cannot really process new definitions and consequences at the same time. I need to really spend some time thinking about the definitions first, and then once I understand and have mastered just what the words mean, then I can try to understand the theorems. So you need to learn, what does normal mean? What does equicontinuous mean? You've got to have all that stuff down cold before Wednesday's class. Okay, so step 2, I was hoping one of you would remember so I wouldn't have to, is let's let f be the set of all f from omega to d such that f of 0 equals 0, f is 1 to 1, and f is holomorphic. Whenever I give you a set, what's the first thing you should ask? Is it empty? How many of you have heard of the Riemann hypothesis? So the Riemann hypothesis says all the zeros of the Riemann zeta function are either at the negative even integers or they have real power half. We'll talk about this later. It is one of the biggest open problems in mathematics. It's one of the millennial problems that Clay has offered $1 million to solving. There are a lot of theorems that talk about how many zeros you have whose real part is greater than a half. I was fortunate enough to have 2 thesis advisors. One of them, Henrik Ivanich, used to say, these theorems can be characterized as the following. People are trying to find better and better estimates for the cardinality of the empty set. I can prove the empty set has at most this many elements. I can prove the empty set has this many elements. We believe the set is empty. We can't prove that. We can prove some things about how many elements must it have. I want this to have at least one element, because I'm trying to show I can conformally map omega to the disk. If this set is empty, I'm in trouble. Is this set empty?
No.
Good. Give me an example.
Step 1.
I'm sorry?
The step 1 function.
But now we've already done it, so now we're assuming omega is in D. So the step 1, the identity. Not empty. Identity is in F. Can you give me a second function? Yes.
Rotation.
Rotations. Can you give me another function?
Contractions.
Contractions. So contraction means we're making it smaller. Alright, we have infinitely many. None of them change the shape of omega, really, in a helpful way. The rotations just, and the contractions, so none of them is going to give us what we want, but at least the set isn't empty. So, step 2 is to show there exists a function f max in F such that f prime of 0 is maximal. So there is some function whose derivative is larger than every other derivative. This is what's going to be long and hard to prove. Okay? So I have no problem assuming that I have a sequence of functions. But maybe I have a sequence of functions whose derivative at the origin is getting larger and larger and larger and larger and larger. This tells us that that can't happen, that there is some function whose derivative is large. Moreover, and f max is holomorphic, it's 1 to 1. I almost wrote another word.
Onto.
Yes, I had to stop myself. It is onto, but what do you think proving onto is?
Step 3.
Onto is step 3. Okay? So there is a function. No other function has larger derivative in absolute value. It is one-to-one. This is exactly what we want. All we have to do now is show that this special function is onto. Okay, so this is where we're going to stop in terms of step 2. I am not going to prove right now the existence of such a function. So this is the opposite of how I did it 3 years ago, and you can tell me which method you prefer. I want to skip the hardcore analysis for now and just say, let's take this fact as given, move on, and then we'll see that it works, and then we'll have some real motivation to come back to that stuff. So step 3, f max is onto. Okay? So now we have one step left. Okay. Any thoughts as to how we prove f max is onto? So you've seen arguments like this before.
Like the O'Shea's argument, the kind where we, like, I remember one time we had to show that every point on unit diff would hit.
Mm-hmm.
You could do something like that.
Okay. We do want to show every point is hit. So if a point is not hit, we want to somehow show that there's a contradiction. But what do you think we're going to contradict? That it's going to be maximal. We're going to somehow show that if a point is missed, it's not maximal. If not, there exists alpha in D, not in f max of omega. It will contradict maximality of f max. Okay? You've seen arguments like this before. If you've thought about like the square root of 2. The square root of 2 is irrational. If you can write root 2 as a over b are relatively prime, what you do is you then get 2 is a squared over b squared. So you get 2b squared is a squared. Therefore a, I can write it as 2 times m. And that's going to imply that 2b squared is 4m squared. So b squared is 2m squared. Therefore b is even. Therefore I get 2 is m over n, which implies square root of 2 is, m squared over n squared. And that contradicts the relative primality of a and b. So I found that if a and b were relatively prime, I found another solution that was smaller. And that can't happen. If you've seen special cases of Fermat's last theorem, Fermat's method of descent, which Euler used very well for some special cases, that shows you if you have a solution that's minimal, you can somehow find another solution that's even more minimal. And you can't do this infinitely often. You have something called like a height. So this is an idea you've hopefully seen a couple of times. So the question is, how do we show that it's not minimal? So we have to find a function that has a larger derivative. Do you know any theorems we have that could give you information about the value of a derivative of a function at the origin, of a map from the unit disk to the unit disk, that sends 0 to 0? Schwarz lemma. So step 3, use the Schwarz. Okay, the whole class was just to say this. Okay? So if we use the Schwarz lemma, we should be able to get a contradiction. And I am not interested in memorizing and impressing you with how well I can memorize things. So let's let f be a function f max. And let's let big F equal c of g alpha composed with g, composed with c of alpha, composed with f, where g of w is e to the 1/2 log of w, think square root of w, h of w is w squared. Think square of w. Okay? So what does this do? If I look at big F of 0, f of 0 is 0. This sends 0 to alpha. I have g of alpha. And then c of g of alpha sends g of alpha back to 0. So f of 0 equals 0. Why am I able to do this? Well, I'm going to assume that alpha is not in my set. My set is simply connected. It turns out we can define a square root function. And so we have a nice definition of the logarithm. So when I apply things here, do I ever have to worry about taking the logarithm of 0? The only thing that could go to 0 is I need to evaluate C alpha at alpha to get 0. Well, how would I get that? I would have to have something that's mapped to alpha. Oh, nothing is mapped to alpha. So the square root function is well defined over here. I'm not going to be defining it on 0. So it's okay. So f of 0 is 0. And now what we do is we say, this implies I can write little f as C alpha inverse composed with h, composed with C of G alpha inverse, composed with big F, and let's just call that phi composed with big F. Do I need to write the inverses here? No. Why am I writing the inverses?
Clarity.
Clarity. Absolutely. I'm writing, look, I've got this relationship over here. I want to write now little f in terms of big F. I'm going to just rattle things off. I apply C of G alpha inverse, then G inverse, which is H, then C alpha inverse. So I'm just applying it like that. And we get phi of 0 is 0. Phi maps the disk to the disk. What can you conclude about phi prime of 0? I'm sorry?
At most one.
It's at most 1. The only way it can be 1 is if it's a rotation.
Wait, can you just clarify that last point a bit?
Which point? This point?
Yeah.
This is now where we use Schwarz.
Oh,
So by the Schwarz lemma, the only way we can have it is if it's a rotation. And phi is not a rotation. So it's strictly less than 1. And now we have chain rule. So the chain rule tells us f prime of z is big phi prime of f of z times big F prime of z. This is less than 1 in absolute value. What can you tell me about f prime at 0 versus little f prime of 0?
Less than.
Which one is less? Little f
Big
prime?
one is less than. Big F is.
Other way around. This is a number less than 1. This is less than 1 in absolute value, but this product equals this. So this is like a half. This would be twice f prime of z.
Less than. Yeah.
So this implies big F prime of 0 is strictly less than big F prime of 0. And this contradicts maximality of little f, which was our f max. Okay? And that's the proof. Okay? I have mixed feelings about this proof. It's using the Schwarz lemma, which I like, but I don't really see what's going on in this proof. So what I want to do is I want to essentially do the same proof now, but I want to spend a little time and thought about looking at what's going on. Okay? So we're going to do something very similar to this. But what I want to do is I want to try to get a feel. We don't actually need the Schwarz lemma. That's the amusing factor. We use the Schwarz lemma, but the Schwarz lemma is not needed. Why is it not needed? I'm applying the Schwarz lemma to this function big phi. Is big phi an arbitrary function that I know nothing about? I know what big phi is. What could I do? Take derivatives, right? There's no need to use the general framework. We have a specific function. It's a composition of three functions. Just take the damn derivative. Now, let's make life easy for us. What kind of number can you assume alpha is? We're missing some number. What kind of number are we missing? We're missing some number in the unit disk. Without loss of generality, alpha is positive real. Excellent. Right? Because we can always apply a rotation. And that's not going to change the value of the derivative at the origin. Because we're going to just multiply by e to the I theta. So, after rotating, alpha is a positive real number. So the square root of alpha, everything's going to be really nice. C beta of z is beta minus z over 1 minus beta bar z. Absolute value of beta is less than 1. C beta prime of z, oh goodness, we get to use the quotient rule, right? It's derivative of the top times the bottom, so it's negative 1 minus beta bar z, minus the derivative of the bottom, minus beta bar times beta minus z over 1 minus beta bar z squared. If you only care about what happens at z equals 0, we could actually just expand the denominator using a geometric series. So we get c beta prime of z is we have a negative 1, we have a plus beta bar z, right? And we have a minus beta bar z, so they cancel, right? And so we get negative 1 plus beta bar times beta, that's the absolute value of beta squared, over 1 minus beta bar z squared. There are two places where we will probably want to evaluate this derivative. What are those two places? What two places would we want to evaluate this? There's two special points for C beta.
0 and beta.
0 and beta. C beta prime of 0. All right, when I put in 0, I just get negative 1 plus beta squared. And this is less than 1 in absolute value. And the other place I might want to evaluate it is at beta. And now I have 1 minus beta squared. So I get negative 1 plus beta squared over 1 minus beta squared squared. Well, 1 minus beta squared squared, this is the same as this with a negative sign. So this is just negative 1 over 1 minus beta squared. And an absolute value, what can you tell me about that? It's greater than 1. So now all we have to do is we look at our functions and we calculate the derivative. And so we can see that the effect of this is we're going to expand the derivative just a little bit at the origin. And so we want to study the effect of this. And so big F prime of 0 is going to be C G alpha prime at G of alpha times G prime at alpha times C alpha prime at alpha times F prime of 0. Alright, so the first is we take beta to be G of alpha. Well, g of alpha is the square root of alpha. So we get negative 1 over 1 minus beta is the square root of alpha. Absolute value squared, so we get 1 minus alpha. Now we need g prime of alpha. Well, g prime is the square root of w. This is why I wanted alpha to be real. G prime of w is 1/2 w to the minus a half. So at alpha, I'm going to get 1 over 2 square roots of alpha. Next, I have C alpha prime at alpha. So that's f of 0 is alpha. Okay, so I think we have another negative 1 over 1 minus alpha. Alpha squared, I think. And then f prime. We're going to have to stop here, unfortunately, which is a pain, but we will have to then finish the algebra calculation.